Well, thank you for that very kind introduction, and thank you all very much for coming. It's a little daunting, partly because you're all backlit, so I'm seeing these sort of dark shapes here. But please, the more people interrupt me for questions, the happier I'll be. So I should probably start particularly by thanking the Institute. As was mentioned, this is the third time I've had the opportunity to be a visiting member here. 1990, 2000, and this year, 2015. As you can see, I have a particular reason to be grateful to the Friends of the Institute. I'm supported as one of the Founders Circle's members for 2015, 2016. And the Institute has always been a kind of magical place to me. I don't know if anyone will understand this reference, but it's been sort of like Brigadoon for me. Every couple hundred years, you know, the mists part and the magical place appears, and I'm allowed to walk in for a year. It's really just been terrific. So let me try to explain to you what I'd like to try to convey is what the area in which I work is about. And I'm not going to try to get to any technical details about it, but just what it is that a lot of us, particularly this year at the Institute, because this is a special year in geometric structures in three manifolds. So what a lot of the mathematics members at the Institute are thinking about in sort of the background of what we do. So let me start with this picture from my current, well, not my very current, my current locale is Princeton, but the place where I live most of the time. This is a picture from the Central Valley of California. And you'll notice that it is flat. I don't know if you've been to the Central Valley, but it is really flat. They're kind of, I think Davis itself is at 12 feet above sea level or something. There are these little bumps in the middle, but basically, there's a reason that farming is a big deal here. It's very flat. And so when we look around us, if we look around us locally on the Earth, it looks flat. Well, not every place, but some places. And that fact that the local information that we see tells us that the Earth is flat led to considerable misunderstanding over the shape of the Earth in the past. So this is a picture of a ship sailing through the Pillars of Hercules off to, well, it wasn't quite clear off to where, because it wasn't quite clear what happened if you went far enough. And in fact, until Magellan, actually this is after Magellan, I'm cheating a little bit, but until Magellan's ship circled the globe, there were all kinds of things that were possible, or people thought were possible, that would happen if you sailed far enough. And these were all really errors of judgment when we looked at local information and tried to figure out what was happening globally based on our local information. And so people thought the Earth was flat, sometimes. I mean, I'm talking now, really, probably 2,500 years ago, people thought the Earth was flat, and then they began to change their view somewhat. Except, of course, there are some holdouts. So here are some headlines from the Flat Earth Society, to which we should all be extremely grateful, because as far as I can tell, it is the last group of people on the planet that it's okay to make fun of. So, and it's not quite clear whether they're making fun of themselves, really, but the Flat Earth Society indeed exists, so the whole world is deceived except the very elect. And my favorite is the last one, the world is flat, and that's that. So there are some holdouts, but really, you know, evidence is against them, I have to say. They have to postulate a gigantic light in the sky and also a very massive conspiracy on the part of most everybody. So anyway, other than the holdouts. So let's move on from the Earth, which we all know what the shape of the Earth is. But it's worth taking a minute to think about how we know that. And the way we know it is that we've been told it since we were little children. We've seen globes, we've seen pictures of the Earth from space. This is information that has been passed down to us. And if all of the technology, the current technology in the world, were just destroyed overnight, you know, the electromagnetic pulse problem, if it were all destroyed overnight, reconstructing that information about the shape of the surface of the Earth would be reasonably difficult. I mean, you would have to actually figure out what it was you were trying to do. And if we couldn't move very far on the surface of the planet, it would be quite difficult to do. So it wasn't, I've just been making fun of the Flat Earth Society, but that's because the Flat Earth Society exists in a time when there's abundant information to contradict their point of view. But for someone living 3,000 years ago, this wasn't a stupid idea that the Earth was flat. It wasn't even a badly informed idea. It was just a local idea that that's what we had. So if we move on to the universe, which is where we live, so I don't remember the date of this picture. I think it's from the 1600s. We're in a very similar situation to the situation that people were in 3,000 years ago. That is, we have very local information. I mean, we can see pretty far, and we can see farther and farther, but our information about the universe is still very constricted by how far we can see and how quickly we can move in space. And that leads us to not have very good information about what the shape of the universe is. And so in this picture, I think we've moved beyond the point where we think that there's a gigantic dome in the sky that's covered with painted stars and we could stick our heads through it, which is what this gentleman appears to be doing. And I guess heaven is past that. That would be nice. But nevertheless, we don't know that much. So here's some questions that we could ask. And speaking of which, you haven't asked any questions yet. So you're polite. Oh dear. I spend my life with mathematicians. I don't know. Well, no, they're very polite. They're just.
Let me just say
yeah.
what I did, which is we will mostly have talk interrupted by questions as people are moved to do so.
Yeah.
For roughly a half an hour, and then we'll have a question period.
Okay.
A formal one where they're on the spot.
Okay. Yeah. Yeah.
And all the things that shocked people about the code, that was the least of it. So when was there Western acceptance of the Earth is round? I mean, when did predate the Earth being flat?
I think it did. I mean, and in fact, the early Greeks knew the Earth was round. They computed the circumference of the Earth. Nevertheless, I would say that the number of people on Earth who were essentially members of the Flat Earth Society probably, my guess is that it dropped to zero, more or less, around the 1600s, because it was kind of hard to believe. But yeah, I think I'm right that the date of the Earth is round and this is how big it is around 250 BC, something like that. So if we go back to the universe, we have to first figure out what questions we can ask about it that are sensible questions. And so here are a few. So one of them is it finite? And it's not even clear what finite means, but let's take it to mean finite volume. Is there a finite amount of stuff in the universe? Does it have an edge, as in that picture that I showed you? Could you actually get to the edge of it and stick your hand through? And if it does, what's past that? Is that possible? Does it curve? This turns out to be quite a tricky question, and I'll try to spend a little bit of time on that. What dimension is it? This is something that really worries physicists. At the moment, I think the popular view is that it's actually 11 dimensions. This is based on string theory. And that's very interesting, and they may be right. I'm not saying they're not right. But for our purposes, we're going to just worry about the three-dimensional space that we can see. So that's the universe that I'm interested in. It's similar to saying I don't actually have to know the dimension of the universe to say that the surface of the Earth is the surface of a ball, right? I don't have to know that dimension. I can ask the question, what is the surface of the Earth? And the answer is it's the surface of a ball. Similarly, I can say I don't care what the dimension of the universe is. I'd like to know what the three-dimensional space that I'm seeing around me is. What is it? And the final question, and this is what people in my field spend most of their time on, or a lot of their time on, what are the possibilities? How can we even try to understand what the alternatives are for a three-dimensional universe and the one in which we live? So I'm going to talk about two of these in particular. Does it curve and what dimension is it? And at the end, I might get to the last one. So let me start with dimension, because dimension is one of those things that mathematicians just seem to take in stride, and other people sort of balk. As soon as you get past 3, people don't like it. So I'm going to explain to you why mathematicians just don't pay much attention, because dimension is dimension. And so this is a mathematically inaccurate way of describing dimension, but it turns out to be a workable way to think about it almost all of the time. So a space has n dimensions if it requires n pieces of information to locate a point in the space. That's it. So let's look at these examples. So this thread, so this is a mathematical thread. It doesn't actually have any width. And if I had drawn, which I should have drawn, a base point, sorry, the laser pointer doesn't work on this wonderful screen, so I can't actually point. If I had drawn a base point on this thread, and then just told you a distance, like 3 inches, we could agree that what that will mean is that you'll start at that base point and you'll move 3 inches to the right on the thread. And if I say negative 3 inches, you'd move 3 inches to the left. That is, I could give you a single number, and you could, without fail, locate a particular point on this thread. And so that's a one-dimensional object. This thing, this circle, there's nothing in here. This is empty. This circle is also a one-dimensional object. I have to be a little bit more careful about base points maybe, so I'll pick a point, let's say right here, but I'll do exactly the same thing. I'll give you one number, say 3 inches. I'm having trouble thinking of any numbers higher than 3, apparently. 3 inches, and you'll start here, and we'll agree that you'll travel counterclockwise around the circle a distance of 3 inches. And wherever you end up, that's the point that I meant. So there are many different ways to describe that point, right? I could say 3 inches or 3 inches plus 2 pi times something. Is this your objection?
Yeah,
Oh.
not objection.
Oh.
Would a Mobius strip also be one-dimensional?
I'm going to get to it. Thank you. Excellent question. And I'm going to get to that. Yeah. So, so this is also a one-dimensional object. This, on the other hand, is a two-dimensional object. And this is the surface of the Earth. I mean, that's a two-dimensional thing, the surface of the Earth. And you all know that it's two-dimensional because you know that you can locate a point on the surface of the Earth with 2 pieces of information. And the 2 pieces of information we usually use are latitude and longitude. There are lots of different ways to do it. I could give you different ways to what's called parameterize the Earth. Every way that I give you to parameterize the Earth, you're going to be able to describe a point on it using 2 pieces of information. So the surface is two-dimensional, but if I actually want to locate a point in the solid part of the Earth, I need 3 pieces of information. So for example, I could give you latitude, longitude, and depth, right? That's 3 pieces of information. That, without fail, will locate a particular point here. So those are the ideas of dimension. And before I get to the Mobius strip, which I think I'm about to get to, this is why we're not so bothered by thinking of time as the fourth dimension, which sounds like this amazing philosophical existential thing. But a different way to think of it is to say, suppose I wanted to meet you in Manhattan. And I said, okay, meet me at the corner of 57th and Broadway. I have no idea what's at 57th and Broadway. But anyway, meet me at the corner of 57th and Broadway, 2 pieces of information, on the 5th floor, 3 pieces of information. Great. What do you need to know? When? Oh. Sorry. Yes, you're correct. Northeast corner. I still claim that's 2 pieces of information. But if you don't want to just wait there forever, seeing when I show up, you need to know the time. So if I want to locate a point in space-time, 3-dimensional space-time, I have to tell you 4 pieces of information. That's all the time as the 4th dimension means to me. So let me see. Oops. The Mobius band. The Mobius band is 2-dimensional. And it's 2-dimensional and it's non-orientable. So for those of you who haven't seen, I expect most of you have seen a picture of a Mobius band. So this is 2 pictures of a Mobius band. I think I actually brought a Mobius band. Hold on, let's see. It's possible. I carry things like, yes, I carry things like this around with me.
You must have planned it.
Yeah, no, I didn't. So here's a picture of a Mobius band. It's just a strip of paper with a half twist in it, taped together. And like all mathematical objects, it's idealized. It actually, you should imagine that the paper has no thickness. So if I want to locate a point on the Mobius band, what do I do? Well, really, if I look at like a core circle here, first of all, I could tell you where to be on that circle with 1 piece of information. And then I could tell you where to be to either side of the circle. So that's 2 pieces of information, again, to locate a point on the Mobius band. The curious thing about the Mobius band, and one of the reasons people love them, is because they're non-orientable. So what does this mean? It means that if I draw a picture of my right hand on the Mobius band, like that, in that spot, and then the hand travels all the way around the Mobius band back to where it started, so back to this spot, remember the thing has no thickness. So once it's traveled around once, it's back where it started, but all of a sudden, it's a different hand. So this leads to a lot of great science fiction stories, because if there's a non-orientable 3-dimensional space, then you would go travel around in your spaceship, come back, and everything would look fine, except that all the writing would look backwards to you, and similarly, you would look backwards to everybody else. That is, your heart would be on the wrong side. So there's some great science fiction stories based on that idea. And this I have no excuse for, except that it's one of my favorite Escher prints. So this is ants crawling on a Mobius band. Although this comes back to something that I was trying to express about the universe, that is, the relation of the size of these ants to the size of the Mobius band is such that even ants eventually would probably figure out where they were, right? They're so big that they could leave trails and crawl all the way around and figure out that they got back to where they started. So their size relative to the Mobius band would allow them to figure out where they were, whereas our size relative to the size of the universe makes things tricky. Okay, so the other thing I wanted to try to talk about is what it means to be flat or curved, because you'll also hear a lot about perhaps the universe is curved, and it's really not obvious what that means, I think. So a table is flat, right? The regular Euclidean plane is flat. And one way to pin down what that means is to say, is to remember this wonderful fact from high school geometry, which is that if you draw a triangle in the plane, you know that the sum of its interior angles is 180 degrees. Probably you all remember this from high school geometry. That's just a fact about triangles, right? It's a great fact about triangles. And it's a fact about triangles that is not true if I look at a two-dimensional object other than the plane, or it may not be true if I look at a two-dimensional object other than the plane. So imagine, I thought I'd have a board to draw in here also, so I have to just gesticulate wildly instead. So, so imagine imagine I have a globe sitting in front of me right now. And I say, okay, well, let's make a triangle from New York to London to the North Pole. And so you could do that, right? I mean, planes do this all the time, right? You could mark New York and London and the North Pole on your globe, and you can't join them by straight lines because the thing is curved, right? But you could join them by as straight a thing as possible, which are called geodesics. And that's why plane tracks always look so funny to us, because they're actually following geodesics. So I do that. I connect New York, London, and the North Pole by geodesics, by as straight paths as I possibly can. And then I measure that's a triangle, right? I measure the interior angles of that triangle. And what's true is that it's never 180 degrees. It's always, you can see it, right? It's a kind of puffy triangle. It's always a little bit bigger than 100. Actually, sometimes it's a lot bigger than 180 degrees, but it's bigger than 180 degrees. And that's reflective of the fact that the whole space is curved. The whole space is curved, right? And we know that. It's not that complicated. But imagine if light was traveling the way the jet planes are traveling, right? Imagine that flashlights, you know, I turn on a flashlight in New York and the beam went straight to London along the track that we know a plane goes along. And I could do that whole thing. I could measure the distance between the angles between those light beams. It would add up to more than 180 degrees. And that alone would tell me that the space was curved. So this is a picture. So this is a very disturbing picture in some sense. And this one I have to use my own introduction here for an illustration. This is a picture of the surface of a donut. So this is very non-intuitive. It's this picture of a surface of a donut. And what I'm trying to illustrate is that there is actually a way to define distance between 2 points on the surface of a donut so that it's flat. That is, the interior angles of triangles add up to 180 degrees. And the reason is that I could build the donut out of a flat piece of paper. And so you have to forgive topologists here, but this is what I mean. I could take this flat piece of paper, and that's what this illustration is, and start taping the edges together. So I could tape the two long edges together like that. And then if this were very stretchy, which you should object to, but don't, because I could then tape those ends together, and the object that I would get mathematically is the surface of a donut. And so if I measure distance between points here, using a sort of natural way to translate them over here, certainly I'm going to find that triangles behave like triangles in the plane. They're flat. So there are spaces that are flat that are not like infinite planes or infinite space. And I see I'm running out of time. Yeah.
In shorthand figure that out, like as compared to the curve and the larger triangle of the airplane? Like if I was just looking at that and saying, oh, it's a curved thing, I don't automatically assume therefore the triangles are larger than 180 degrees.
No.
So what is the distinguishing factor?
And that turns out to be quite a difficult question, actually. And so it turns out that the topology, that is, the things about the space that aren't related to how it's sitting there, topologists are the people that are said not to be able to tell the difference between a donut and a coffee cup. We can, really. But the topology of the space is connected to the geometry, which is about measuring distances in the space. But the connection is actually both interesting and difficult. So it's not easy to tell if you're sitting there what it is you're sitting on. I don't know if that helped.
Is there a mathematical name in conventions of mathematics for a donut?
A torus. Yeah. So anyway, the news from that one is the torus is flat, and I'm going to have to breeze through a few things. Possibilities for a three-dimensional universe. Well, the one that we think of, I think, and I think physicists even, I don't know what physicists think, is just a three-dimensional version of the plane of the table. That doesn't seem correct, actually. Here's one, and I think I'll try to end with this. Here's one possibility, which is also almost surely not correct, but it sort of leads to ones that might be more correct. What I want to just try to describe in a minute here is the three-dimensional version of a sphere. So here's a sphere, right? This is like the surface of the Earth. We're good with that. Here's what I would call a one-dimensional sphere, which everybody else in the world would call a circle. And we operate a lot by analogy in math, and so we can actually see a three-dimensional sphere quite easily, it turns out. And the way to realize that this is the right thing to do is, let's think about the surface of the Earth and the fact that if I cut it along the equator, I just get these two disks. And one of the things that you do when you're making a map is you take those two disks and you take them over to your plane and you squish them flat. And then you have a picture. And you have a really good picture, actually, of the surface of the Earth. Right? It's just two disks in the plane. You cut them out, you glue them together, you get your globe. Right? That's it. So this is exactly the same thing, except one dimension up. So if I had a three-dimensional sphere, I could cut it into two three-dimensional balls. These are now solid. And I could glue them together. And that's a space. I mean, that's some kind of a space. And it's a space with a lot of nice properties. So remember, when you're traveling along the surface of the Earth, you don't like get to the equator and there's like a big blue line and says you're crossing the equator, right? That's invisible from the point of view of the actual space. Same is true here in the three-sphere. If I'm traveling around the three-sphere, there's no edge, there's no boundary, and it's finite. I mean, it's got finite volume. It's a very elegant space. It would be my personal favorite for a choice for the three-dimensional universe. But it has a problem, which is it's curved. That is, yeah.
Why is the Earth not three-dimensional?
If I think about the solid Earth, it is three-dimensional. Okay. So I just mean the surface of the Earth. I'm just talking about the surface in this picture. Thank you. But in this picture, I'm filling it in. And I'm saying I can get a three-dimensional space just by gluing these guys together along their boundary, as though I were making an atlas, right? If this is like, if I'm going from here to here, it's like I'm traveling from page 47 to page 51 in the atlas of the world. I don't notice that when I'm traveling. It's just I've cut the world up into pieces. Well, here I could cut the universe up into pieces, and each one of them would be a ball. Another nice feature is that if this is like Princeton, New Jersey here, and I send a rocket off straight into space, well, it would have to be a really good rocket and really fast. But in principle, it would actually come back to where it started, just the way Magellan's ship did. So it's compact, but it's curved. And you can actually, yeah. No, please.
Is there a convention, usually when you hear about potentially inhabitable planets and so forth, they talk about in this part of the galaxy and so forth. But is there a convention like with GPS or longitude and latitude for where you could actually find that planet or that sun?
For pieces of the galaxy, that is a question I don't know the answer to. I'm sure there is, but I don't know the right answer to that. And also, I'm making gross simplifying assumptions here, like space is what's called homogeneous. I'm not worrying about black holes. I'm not worrying about local curvature. I'm just looking at the whole global picture. So, as I say, S3 would be my personal favorite, but the problem is that the universe appears not to be curved. And we can actually see that by essentially doing what I described by sending flashlights around the Earth. As closely as it has been measured so far, it looks like it's flat. So let me conclude here by just flashing one.
Could I just ask
Yeah.
a question about that?
Yeah.
What would, if you can give us a preview, some comment, in fact, what would S4?
S4 I can't draw you a picture of. I can give you many descriptions of it. And the description that I would give of it, so this is, I think of this as two three-dimensional balls glued together along their boundaries. That's S3. S4 is two four-dimensional balls glued together along their boundaries. But I can't draw you a picture of a four-dimensional ball, so that's kind of a problem.
But you, mathematically, you could
Absolutely.
draw it.
Yes. Right.
Thank you.
Yep. So these are some of the advantages, I said. These are some of the disadvantages. Let me conclude just by saying there is a three-dimensional torus. This is a picture of it. It has a lot of the advantages of the three-dimensional sphere. It's compact, finite volume, and it has an additional advantage, which is that it's flat. That is, triangles look the way we think triangles should look. And I think I better stop there. Yeah, there's some very interesting questions about how light would have to travel in a torus, but
You know, it may be slightly more interesting to all of us if you just did a couple more interesting things, because our questions may not be as interesting as your answers.
well, okay, so let me just describe, this is also, let me just, the three torus is really a beautiful object. And it's actually not very difficult to visualize because we're sitting in a model for it. So if I go back to this picture, let me explain what I mean by this picture. So imagine that the whole universe is this room. This is it. This is everything. And those people are going to walk out that door. And if this were the three torus that we were living in, they would instantly reappear over there and walk in that way because there's no other place for them to be, right? And if it were the three torus and I could rocket straight up here, then a moment later you would see my head coming up out of the floor. And so on, right? So it's sort of like a giant Pac-Man game. I don't know if that makes sense to you, but Pac-Man with everything glued together. So when the little eating guy goes out, I don't play Pac-Man actually. When the little eating guy goes out this way, he reappears over there like that. And you could get used to that. And so that's not likely, right? We're pretty confident there's actually a dining room out there, right? So this isn't the whole universe. But it's conceivable that on a gigantic scale, this is the whole universe. I mean, that the whole universe is essentially like a gigantic box with its edges glued together. How would we tell? Well, one way to tell would be to send off a rocket, right? If this box were gigantic, if I'm a rocket and I just head out that way, eventually I'll come back to where I started. That's hard. Rockets are hard. Another way to tell would be just to look. That is, if light's going to travel along straight lines, and I'm standing here, and the universe is just this box, and I look that way, does anybody see what I have to see? I have to see the back of my head. I have to see myself. Okay, but if the universe is a gigantic box, what I'll actually see is whatever was here quite a while ago, right? There's a time problem and light traveling problem there. But one of the things that some of the satellites are looking for that we've sent up to look at questions like this is essentially when you look in different directions out in space, are you actually seeing the same object? Are you seeing yourself? Are you seeing the same object? So one of the satellites is looking for matching rings. There's a reason that they're looking for matching rings, but essentially that's what they're looking for. Are they seeing the same thing while looking in different directions from the same location? So this is my personal favorite. I'm sure there are very good physical reasons why this isn't it. But yeah, so let me end there and just end by saying this is one possibility. There are an infinite number of possibilities. So one of the things that I do is look at the whole set of possible three-dimensional objects that there could be. Yeah.
Are you looking for mathematical proof to say this?
No. So what we're doing, I think, is one way to think of it is we're developing the mathematics to say, if this is what it is, this is what you should be seeing. And so that fact, the fact that I mentioned that some satellites are up there actually looking for very specific matching in different directions is directly related to just a straight mathematical study of three-dimensional manifolds. What has to be true if this is what it is that we're living in.
So at this point, it is all theoretical. It hasn't any basis in, well, like, and it has no mathematical conclusion. It is only.
There is no conclusion, yes.
You're looking for the evidence, and then you will look then for the conclusion?
No, I mean, we're compiling the possibilities, and they're looking for the evidence. And then at some point, hopefully, there'll be a synthesis of these two approaches.
But there's no way to do it mathematically.
There's no way to do it straight mathematically, no. I mean, it could be, you know, the universe, but for mathematical reasons, could be this, could be infinite three-dimensional Euclidean space. It still could be a three-dimensional sphere on a scale so large that the curvature isn't detectable by us on the scales that we're operating on. But that margin is getting down closer and closer to zero. So.
Let's move into the
Yeah.
other side. We're morphing into it anyway, and that's good.
Oh, wait, that was a good picture. Sorry. No, I don't think that this is true, but I like the juxtaposition there. Okay.
But I suggest that you point at people who have questions.
Sure.
We all ask as we wish, and if we have enough time, we'll get them all in. We probably won't, and so let's try to keep the questions as succinct as we can, and you keep your answers as long as you want.
Okay. Yeah.
So, in your S3 model here, you say, imagine gluing all the boundaries together.
Mhm.
Excuse me, sometimes it's hard for
Can I ask my
the rest
question?
of us to, I just wanted to ask if you keep your voice up, it's acoustic, so it's hard.
I wasn't speaking loudly.
Yes.
Oh, okay. In your S3 model,
Yeah.
when you talk about gluing boundaries together, do you mean just the boundaries where they touch each other in the equation, so to speak, or you mean exactly around?
No, the whole thing, which is why I can't draw you a picture of the whole thing, because I can't do it, right?
Maybe question number 2 is, when you block out that way and eventually you appear that way,
Yeah.
that turns out to be the model, it's generally imperfect. What happens to atoms and molecules of the body again from there to there?
Well, time is like an additional question, which is why you get into the question, if the whole universe is this room and I look this way, then I'm going to see the back of my head, because the distance from here to here in the model is quite short and light is pretty fast. But if the whole thing is huge, then the back of my head will be long gone by the time, or I'm getting time backwards now, but you appreciate the distinction. And so I'm not trying to suspend time or say it doesn't exist. It's like, it literally adds an extra dimension to the problem that I'm not addressing at the moment. And that would account for decay and so on. Yeah.
What are examples of infinity in what we know physically? Are there any examples that we know of that prove that infinity exists? And the reason I'm asking it is, it seems like the Mobius is the only way to explain infinity. It goes on, but it keeps wrapping around on itself.
Yeah.
That seems to be logical, but I don't,
Well, I think it depends on what you mean by an example of infinity. I mean, we have the integers; they seem to be infinite, right? But I think you're asking about a physical infinity, and you know, the best. I agree actually that this is somehow it's conveying something about that idea to us that other things aren't, but we have a philosophical idea of infinity because we routinely say let's look at the plane. And when we say let's look at the plane, we don't mean let's look at a little piece of the plane. We mean let's look at the whole plane, which of course doesn't really exist, right? But nevertheless, everything works as though it existed. So it's a question of it's partly reality versus you know, this Platonic mathematical world here. So yeah, and I'm not sure.
Plane, I mean, when using your example of the flat world,
Yeah.
it seems like we're just too small a space to see what the plane does.
Possibly, yeah. So an infinity that you can hold in your hand. I feel like there's a poem here, right? Is there not? Something about infinity in a grain of sand, right? But that you can hold in your hand. This is, in some sense, probably the closest we're going to get, yeah. Yeah.
In your introduction, you also mentioned that there might be some thought about other dimensions. Are you working on that?
Me particularly, no. So there's this very, to me, very intriguing split. And so first of all, I should say the physicists doing string theory are actually, there's in some building over here. They're quite separate from what I do, although there's a lot of interaction between some people in low-dimensional topology and what they do. But in topology itself, which is this subfield of mathematics that I do, there's this, to me, fascinating split between people that study things that happen in dimensions 2, 3, and 4. And we're thinking of physical time, it doesn't matter, but a physical dimension 4 is a safe way to think of it. And people that study things that happen in dimensions 5 and higher. And so those tend to be called algebraic topologists, and we're geometric topologists. We talk to each other occasionally, but not happily. And the reason that there's the split is that mathematically there's this whole toolbox which works beautifully over here and fails completely over here, and vice versa. So the split is exactly at 4 dimensions, which is very cool, I think. But so the answer, that was a long answer, and the short answer is no. I very unhappily will work in 4 dimensions. In fact, I am working in 4 dimensions at the moment because I can't really, my intuition is not as good there. But once you get past that, I'm hopeless. So, yeah.
I asked this question of somebody who was dealing with black holes.
Yeah.
And dealing with Big Bang,
Mm-hmm.
not Big Bang. And they're working on physics now to try to get behind the beginning of Big Bang.
Yeah.
This is a while back. Did 3 dimensions begin? In other words, the question has to do with, is that something that began, had a beginning? And then is there a context for 3 dimensions? In other words, this thing, you're going out here and coming back in.
Yeah.
But is all of that in a context of some kind? Or does that question even have any substance enough to relate to what you're saying?
Well, I think that you're just getting beyond my area of expertise. So the Big Bang, let me give you my picture of it. There was nothing. And then instantaneously there was something. So this is we're almost getting into a religious question here, right? So this is tricky, but infinitely close to the moment of the Big Bang, the three-dimensional universe existed, I would say. We can't see it because of the light problems with light, but there was something there. Essentially, the entirety of the universe was there. And so, going back before that, I don't really know what they're talking about.
Well, what I asked, I said, what bang? And the guy said, the physicist said to me, everything.
Yeah,
In other words, it wasn't, I was looking for a little P, and then before there was something that collided with it, and bang. But he said,
nothing. No, there was just nothing.
It was everything.
It was so. Here's one way. Here's one way I sometimes think of it. That imagine the universe is actually one-dimensional. We know it isn't one-dimensional, but suppose it's one-dimensional and it's a circle, right? So, oh, thank you. Wow, look at that. This is such a great place. So if the universe were one-dimensional in a circle, this would actually not be such a bad picture of what, at least the common idea of what's happening and what happened at the Big Bang, which is here's the Big Bang. There isn't anything outside of this object. There's nothing to bang into. There's the only thing in existence is this kind of cone thing. And what's happened since the Big Bang is that the circle has just gotten bigger, right? So as time progresses, the circle has been increasing in size since the Big Bang. And it gives you all kinds of ways to picture, this is not going to answer your question, right? But if imagine I'm an ant living on this circle and I shine a flashlight at my friend, Joe over here. What happens? Well, the light actually doesn't live here. That beam of flashlight doesn't live here. It lives here. It takes a while to get to Joe. So the track of light is captured in this model, but I don't think it really answers your question because it doesn't explain what was here, right?
I don't even know what I'm asking.
Well, no, but
It sounded like a question.
it's usually a good thing. It's a good thing if you don't know what you're asking. Actually, a lot of the time, really. No, I think it's a hard thing for us to wrap our minds around. Yeah.
And mathematically, we know that it's expanding constantly and getting faster.
At the moment, I think we know it's expanding. I think that one of the things that they're worried about is there's no particular reason it has to, right? It could contract for a while, and then it could expand some more, and then, well, this is some kind of
Which could
big
lead-
unbang, right? Where we,
That leads to the possibility of the bang was just the transition between total shrinkage and total expansion.
oh, you're going to make it wrap around that way.
Yeah.
You should be a topologist. Yeah, this is good. It's a good idea. I like it. Yeah. I haven't heard it, but yeah.
Could you point us in the direction of where to find out more information about the transition between the fourth and the fifth dimension, and what are the causes of the difference?
That's a very good question to which I don't have a good answer, but I'll try to think of. No, really. I think it's something that it's well known among topologists, for example. But I don't know that first of all, I don't know that there's any really good explanation. The general explanation. What? Right, but I don't think there's even a good explanation among mathematicians. Among mathematicians, the explanation tends to be, well, once you get to 5 dimensions, there's so much room you can do all this stuff. And that's about the level of the explanation. If I think of any place to direct you, because I do think it's this very cool point, but I don't personally even know a really good explanation of why that's true. So, yeah. Sorry, did I?
Is there a question about
I have one.
Yeah.
Very elementary. Your
My
first
favorite.
entry on your first slide that says the universe finite.
Yeah.
Is all this talk and questioning about whether the universe is a particular shape, expanding
I think a lot of it does. There's a lot of rather confusing and conflicting information about this. And so if you look at, I think, even NASA's website, they seem to say, well, so they tend to divide the universe up into how it's curved. Is it flat? Is it curved like a sphere? And there's which is called positively curved, or is it negatively curved? And does it do this thing? But they don't actually usually address this question. Finite isn't really the right word. The right word is compact. And so they don't really address this question of whether the thing is compact or not. So I'm not sure what their underlying assumptions are there. Yeah.
I just wanted a question about expansion. Do the laws of physics explain how something that explodes can accelerate, keep accelerating? Is that mathematically proven now?
This I don't know. I mean, this you really have to ask a physicist.
Yeah.
I'm stretching here, but I'm still stuck on your idea of making that. Anyway, that's good. I like that.
Other questions?
Before I say thank you, anything else you would like to impart to us is okay.
I don't think so. I guess I'd like to reiterate that this is an amazing place, and I know I'm personally very grateful for what you all do for it. But I know everybody is. It's really just an incredible opportunity for the visiting members to come for a year and get to talk with all of these fantastic people and get to do stuff. So thank you.
Thank you very much.